Welcome, everybody, to Bennu and back, OSIRIS-REx Asteroid Sample Return. I am so excited to be here with all of you all around the world tonight. We have quite the event for you this evening. So many things are happening simultaneously, and we're so excited about this because it brings all of us together to celebrate a mission that has been so successful on so many accounts and has a very exciting milestone upcoming here in 2 days, which is what we're celebrating tonight a little bit in advance, which is the sample return of the pieces of the asteroid Bennu that will be hurtling through the atmosphere towards the Utah desert very soon. I'm spoiling the story a little bit for you, but I want to give you a little bit of excitement as to what is to come. So, yes, we're here. It's awesome. Fantastic. So what are we doing tonight? This is a domecast, and what that means is that we are coming to you live from Salt Lake City here in Utah, from the Cosm Experience Center. We are also having a full dome live stream for various friends and planetariums all around the world, and we're also streaming live on YouTube. So tell your friends, even if they aren't in the awesome dome that you are, they can still tune in, and that's very exciting. So let me introduce myself and my colleagues on behalf of the Intuitive Planetarium at the U.S. Space and Rocket Center in Huntsville, Alabama, home of Space Camp, of course, and Cosm, Inc. here in Utah. We're thrilled to welcome you to this event. My name is David Weigel. I'm the Planetarium Director at the U.S. Space and Rocket Center. Joining me today is Solveig Irvine, who is part of the OSIRIS-REx team, and Brittany Kundert, who is part of our Intuitive Planetarium team. And there are plenty of people here who you can't see who are helping with all the technical aspect, and I've really just given you an enormous introduction to let all the people who are filing into your planetarium late get seated. So you're welcome. You're welcome. All right. So with that, let me let Solveig tell you a little bit about herself and her role in the mission, and then we'll introduce the various team members who are going to be joining us through previous interviews that we did in the last week or so.
Thanks, David. So my name is Solveig Irvine. I'm the Planetary Missions Program Office Mission Manager for the OSIRIS-REx program. And so it's a very exciting thing to get to watch this and be part of this. I'm looking at my dome here. It's just amazing. And I've been part of the team for a few years now, and my job is to make sure that everything goes well with Dante and the rest of the team as this sample comes back.
Fantastic. All right, so first up, let's hear from Dr. Jason Dworkin.
My name is Jason Dworkin. I've been a project scientist well before launch and started out as a deputy project scientist and became project scientist. So I've been on this mission or the precursor missions for 19 years now. So my science actually begins with sample return. So I'm very excited for what's going to happen and what surprises Bennu will have in store for us.
My name is Dani DellaGiustina. I'm the Deputy Principal Investigator for NASA's OSIRIS-REx mission, and this is NASA's first asteroid sample return mission. I have been involved on some incarnation of the OSIRIS-REx mission since 2006. I actually got my start on an earlier, a predecessor kind of prototype version of this mission that was just called OSIRIS when I was an undergraduate student at the University of Arizona. And unfortunately, that version of the mission was not selected for flight, but it in the end was a really positive thing that we were eventually selected to be part of NASA's New Frontiers program, which allowed us to send a much more powerful spacecraft with more scientific instruments to this little world called Bennu, so that we could more fully study it before we gathered a sample from the surface.
All right, and lastly, I need to introduce the PI of the mission, the Principal Investigator, Dr. Dante Lauretta. And he would have introduced himself if I had asked, but when I interviewed him, I didn't, so I will introduce him for you. He has been involved with the mission for quite some time. He is the visionary of the mission. He is in charge of, well, everything. And he was so excited for us to do this event for you, wanted to attend tonight and couldn't. And so we are excited to share this on his behalf. And I'm appreciative to Jason, to Dani, to Dante, to Solveig, and to all of you for being here, and also to NASA Marshall Space Flight Center's Planetary Program Mission Office, who is helping us put this whole thing together. We appreciate all of you. We should get started. Okay, so this is a conversation that we're having about asteroids, about these little tiny worlds in our solar system, these tiny building blocks of our solar system. And in thinking about that, we really need to perhaps dive in a little bit more to understand, one, what those even are and why we care and why this mission is even relevant. And I just digress. Let's go.
So during the birth of the solar system, as material was present in this disk of dust and gas that was spinning around the young sun, there were a lot of processes that took place, and a lot of that material that was present in that initial disk, it eventually accumulated into the modern day planets. What is left over from that process are the asteroids. They're the debris that remains after planet formation. And so when we have the opportunity to look at these objects, to take a sample from them, we are truly getting a look into a time capsule, and something that there's no other way to do this but sample return. So it's an incredible privilege, and to have these missions operate, and we're really lucky that we have a space agency that can pull something like this off. And I really do think the results from this mission are going to teach us new things about the origin of life, the origin of water on planet Earth, and there's no other way to really get at this information except going out there and taking a look at these ancient relics of planet formation.
All right, thank you, Dani. So one, I should also highlight something really nicely here. I know we're talking about the OSIRIS-REx mission, but the simulation that we put together, this sort of early formation of our solar system, is actually using a backdrop from the Tarantula Nebula as viewed by the James Webb Space Telescope, and I think it's really stunning. And as we go into, trying to better understand our own solar system with these various planetary missions like OSIRIS-REx, we're also trying to better understand planetary formation with other missions, and we're not going to get into that. I just think it's fun. Okay, cool. So let's do this. Let's take a look at our solar system as it is in present day, and let's start with something very bright. This is, of course, the sun, and it probably helps to give you a little bit of perspective as to how big things are here if we turn on maybe some planets' orbits, just so that you get a sense of where we are in things. So we'll get that toggled for you here. And when we're looking at sort of the structure of our solar system, space is so very, very big, right, that we can't even see these enormous planets unless we have a little bit of perspective with orbit lines, which of course are not drawn in space. But let us also take a look at where the asteroids reside, these tiny building blocks of the solar system that Dani was talking about. So the main belt of asteroids resides between the orbit of Mars and the orbit of Jupiter, and you can see this population kind of nicely spaced out in here right now. We've discovered millions of asteroids to date, but the main belt is, I guess, well, the main concentration of asteroids, but there are plenty more asteroids that we see in our solar system. So to give you a little bit of perspective of that, well, here's more. The colors represent different families of asteroids, but you can see that, again, they reside mostly in the same region of space, although some get a good bit closer to Earth than you might like. More on that in a moment. And further, let's take a look at some of the outskirts of our solar system. We also have some smaller bodies as well. Ooh, let's see. There we go. Are you tracking? I clicked the wrong button. Okay, cool. Sorry, got it. Amazing. Thank you. Okay, so now you're seeing all these pretty things that I was telling you about. Good, good, good. Okay, so as we're taking a look at the outer solar system, this is the Kuiper Belt. This is sort of residing outside of the orbit of Neptune. This is giving us all these small, icy, rocky worlds, maybe more icy than rocky, mostly comets. Asteroids, though, are going to reside in that more inner solar system between the orbits of Mars and Jupiter. And actually, Brittany, as you're flying, if you'll take us in just a little bit, since we didn't let people see that. So we'll zoom in for a little bit closer of a look. There you go. Fantastic. So you can see, again, the colors that I was mentioning, which are the different families of asteroids. You can see that this resides between the orbits of Mars and Jupiter, and that Jupiter is actually shepherding some of these families along, and we call these the Trojans. That's what's visible in blue. And Jupiter's orbit is that one sort of right in our field of view. All right. So what we're going to do now is get a little bit closer look at the Earth. So if you'll hang in with me, hold on to your seats, and let's zoom in for a closer look. The reason we want to talk a little bit about the Earth is because when we talk about the need for better understanding asteroids, there are so many things that are involved, and I think that really goes into the OSIRIS-REx acronym itself. So I'm going to tag Solveig in to tell you a little bit more about that and sort of why OSIRIS-REx is a priority for us.
Thank you. Thanks, David. So yes, so OSIRIS-REx, it's a unique name, and it's actually an acronym that spells out the main goals of the mission. So it stands for Origins, Spectral Interpretation, Resource Identification, Regolith Explorer, which is a huge name, which is why we shortened it to OSIRIS-REx. And it talks about, within that acronym, it talks about our goals of the mission. So the origins, the prebiotic chemistry that happened way back in the atmosphere, before we had atmosphere, before we had people, what did that look like? And so the origins of life come from the OSIRIS-REx, from Bennu. Spectral interpretation, resource identification, we wanted to map the asteroid, figure out what it has, what it contains. And I guess I've missed one, didn't I? Security. Security is the second S in it. And security for our planet. I know Dante talked a little bit about, or we will talk a little bit about the Yarkovsky effect, but also planetary defense is important. So we need to understand the behavior of these near-Earth objects so we know how to defend ourselves if we would have to. And lastly, the Regolith Explorer part, bringing back that sample of the regolith material, the surface of Bennu. And so that's why we named it OSIRIS-REx.
Awesome, thank you. So what we're looking at in here right now, this beautiful blue here that's casting a glow on me, is a shell that's about 500,000 kilometers in diameter, and this is representing a region of space around the Earth that we don't really want asteroids to venture between it and us, right? We are very much in interest of protecting ourselves here on the Earth. If you heard about the dinosaurs, well, they didn't have as good a time, 65, 66 million years ago because of one of these things. And so we really want to pay attention to these small bodies in our solar system, but it's also a little bit hard to do so because they are rather small. They're extremely dark, as we'll see here momentarily. And so what's represented here is flybys of the Earth. There's 256 mapped in here from 1900 to 2200. So anything that you see that is a white point here has already happened. Anything that is red is going to happen in the future. And our cutoff size here is a little bit over 100 kilometers, or excuse me, 100 meters in diameter for the actual asteroid itself. So even an asteroid that is smaller than that is something that certainly can pose a threat to us. And this is part of why we're very interested in OSIRIS-REx and other asteroid missions like DART that took place almost a year ago today, which gives us a better understanding of how these asteroids operate and how we can protect ourselves, as well as go through all the other acronym pieces of things that we're interested in. Cool. So let's take a look at, now that we understand sort of what the mission of OSIRIS-REx was intended to be, let's take a look at its beginnings in 2016 when it launched. So let's slow this to a stop here.
One. And OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Plateau has begun to ramp off. Current altitude is 14 miles.
And beautiful view of the OSIRIS-REx spacecraft on its way out into space towards the asteroid Bennu. But why did we choose Bennu? That's actually a really good question to consider. So again, let me give you some perspective with some of these planetary orbits. And let's take a look at Bennu's orbit as well. So Bennu's orbit is this green line. So we'll zoom out just a little bit here. And Bennu's orbit is really ideal for us, but rather than me telling you, let's go talk to Dante to tell you a little bit more.
Bennu was selected as the target of this mission all the way back in 2005. And when we were first coming up with the concept for the mission, the initial constraints were based on the engineering. We needed an asteroid that didn't get too close to the sun, because we didn't want to have to deal with high temperatures and an expensive thermal control system. We also didn't want to get too far away from the sun because we were solar powered and we wanted to be able to generate enough electricity to power all our instruments and all the electronics on the spacecraft. So that eliminated a large number of asteroids. We were looking something that maybe got about 80% closer to the sun than the Earth does to maybe about 40% farther away. The next constraint came from the fact that we have to bring a sample return capsule down to the surface of the Earth. And the steeper the angle between the orbit of the asteroid and the orbit of the Earth, the higher the speed that it enters and the hotter the capsule will get. We really couldn't handle coming in any more than 10 degrees off the Earth's orbital plane. So we needed something that had basically a very Earth-like orbit. And then we started to worry about the size. Right around that time frame, astronomers were learning that asteroids smaller than about 200 meters in diameter spin incredibly rapidly, some even more than once per minute. And we thought if something was spinning so fast, it would be really hard to get a spacecraft to the surface, and it probably would have flung all the loose material out into space anyway, so there'd be nothing for us to collect. So we needed something bigger than about 200 meters. And at that point, we had just a few dozen asteroids to select from, and science finally got to play a role.
We think that asteroids like Bennu that are chock full of carbon, organic molecules, and also hydrated minerals or water-bearing minerals are really good representations of the types of objects that delivered some of the prebiotic ingredients that we needed for life to start on Earth to a very early version of our planet.
Bennu rose to the top of the list because it flew very close to the Earth, both in September of 1999 when it was discovered, and again in September of 2005 when we were making that selection. And we collected a phenomenal amount of information using telescopes all over the world and in space. It became the best telescopically characterized asteroid in the solar system, and all of that knowledge really helped facilitate our mission design.
All right, fantastic. So this is our first view of the asteroid Bennu, and let's take a quick look though at what Solveig was talking about with the Yarkovsky effect and some of these intricate forces at play that can change up the orbits of asteroids more than you might expect.
Look at the future orbital path of small asteroids like Bennu. Surprisingly, it's not just gravity that influences where they're going to go. Other forces start to play a role, most importantly, a phenomenon known as the Yarkovsky effect, named after the Russian engineer who first conceived of this idea. And what happens is a dark asteroid like Bennu absorbs a lot of sunlight. Think about a parking lot in the middle of summer, right? It gets really hot. And when you go out, even after the sun has set, you can still feel that heat radiating off the asphalt. The same thing happens on Bennu. It gets very hot, and then as it rotates onto its night side, it releases that energy back into space as infrared photons. And that imparts a small thrust on the asteroid. Because Bennu is a retrograde rotator, that emission is in front of it, so it acts like a brake and actually slows down its orbital velocity, causing the semi-major axis to shrink, making it march inward into the inner solar system. And this is, in fact, the mechanism we think that led to Bennu leaving the asteroid belt and entering into near-Earth space.
So before we leave this behind, I think this is just a really fascinating idea, a fascinating concept, right? Because here you have some object that is so tiny that these minute forces on it can have such an enormous effect on its positioning in our solar system. And, you know, that's a little bit scary to think about in terms of our safety again. But it's really amazing that we know about this and are able to better understand it with spacecraft like OSIRIS-REx and soon to be other asteroid missions, so that we can better prepare, but again, better understand how things in our solar system came to be the way they are and how they're continuing to change throughout time. And again, I think it's just a very intricate piece of science that's really a really fun thing to convey to everyone. So how does OSIRIS-REx explore things like the Yarkovsky effect, explore things like the asteroid Bennu? How does it map the surface? We need to look at some instruments. So let's jump right in. What you should see coming up right here shortly is a beautiful spacecraft that is a little bit bigger than a person per se. And I now want to turn it back over to Solveig to tell you a little bit more about the various instruments on board.
Thanks, David. So yeah, so we have several instruments that help us figure out what's going on at Bennu. We have and they're all acronyms, of course. We love our acronyms. OCAMs, which is it's a three-camera suite, right? So we have our PolyCam, which is an 8-inch telescope. We have our MapCam, which does high-res images. And we also have our SAMCam, which does the global imaging and mapping. So we use these three cameras to map the surface of Bennu that you see here. We have our OLA, which is the OSIRIS-REx laser altimeter. It's a scanning LiDAR. It's very similar to radar, but it uses light waves instead of radio waves. And that was actually designed by the Canadian Space Agency. We also have our OTES, which is the OSIRIS-REx thermal emission spectrometer. And this looks for minerals and temperature information by collecting infrared data from the surface of Bennu. This was developed by Arizona State University. We also have OSIRIS, which is the OSIRIS-REx visible and infrared spectrometer. And this looks at visible and infrared wavelengths, and it was developed at Goddard Space Center in Maryland. And lastly in our instrument suite, we have our REXUS, which is our regolith X-ray imaging spectrometer. Looks at X-ray fluorescence line emissions. And this was actually a joint project developed by students and professors at MIT and Harvard, and was able to fly. And they actually were able to find a black hole with this, which was a really neat discovery.
Not a main mission goal.
Not a main mission goal, but just another side fun thing that we had that we enjoyed from it. We also have our TAG-SAM, which is our touch-and-go sample acquisition mechanism. It's essentially the very long arm that we used to navigate down and take a sample from the surface of Bennu. And you can see our TAG-SAM head on the bottom. That's actually our filter container that collects the sample. And last but not least is our sample return capsule, which is what is returning with the sample of Bennu on Sunday. So very soon it's going to be landing in the Utah desert, and we're going to be able to open it up and see what's inside.
Fantastic. Thank you. All right. So again, to give you a sense of scale, you might be wondering, well, if I was floating in space with this beautiful spacecraft, how big would I be? Well, I modeled this astronaut to your size, whoever you are. Yes. All right. Cool. Continuing, let's dive in a little bit more to this asteroid, shall we? So what I'd like to do now is get a little bit up close and personal, and we're able to get up close and personal thanks to the intrepid mapping of OSIRIS-REx, right? So one of the first things that happened was when OSIRIS-REx was first sort of observed, it was very, very different than we initially expected. So let Dante and others tell you a little bit more.
I like to refer to Bennu as the trickster asteroid because it has challenged us every step of the way. The first challenge arose when we got the initial images of the surface. We had studied this thing with space telescopes, with ground-based telescopes, with radar, infrared, visible, and we had convinced ourselves that it was a really smooth, kind of sandy surface because surprisingly, it heats up and cools off very quickly, very much like beach sand does. And we said, okay, we're going to Bennu Beach. I literally said that many times when we were designing the mission. And of course, when those first images arose, it was rough and rugged and rocky and covered in giant boulders, exactly the opposite of what all of our scientific analysis had suggested. So instead of these broad, smooth areas where we could safely send the spacecraft in to collect a sample, all of a sudden we had to get into these tight little craters, which were the only areas where we could see particles of the size that our sample collector could pick up, which is about 2 centimeters in diameter or smaller.
Awesome. Thank you, Dante. Okay, so before we zoom into this extremely high fidelity model, how do we get an extremely high fidelity model? Well, again, it's because OSIRIS-REx was able to map with incredible fidelity. So what I want to show you is a look at the various orbits, orbital trajectories of OSIRIS-REx around Bennu. These are color-coded by mission phase, which you can see highlighted at the bottom of your screen there. And so we start with our approach, preliminary survey. Now we're into orbit A, getting into detailed survey here. Continuing on and on. And one of the things you'll notice is that there's some very sharp angles in here. And you might be thinking, wow, like you really messed up these trajectories. That doesn't happen. And quite the opposite. This is extremely accurate representation of the orbit. So what are we looking at? Well, these are the locations of various sharp burns that were needed in order to course correct and reposition the spacecraft such that it can perform the various needed mappings of, again, the asteroid. So when we try to go into orbit around an object that is as small as Bennu actually is, well, we have to be very, very careful with the way we're thrusting and continually thrust in order to get the orbital mappings that we need, right? The orbital trajectories that we need. The gravity at Bennu is like 1/10,000th that of the Earth. It's very, very, very tiny. And so you, standing on the surface and jumping off, you could. You could. That's a crazy thought, right? Like, you wanted to dunk, you can't even dunk. You can't come back home. You're just launching off into space. Wow. So, Solveig, did you have anything else you want to say orbit-wise?
I mean, no, just it took a tremendous amount of effort. The team was phenomenal. And we did the preliminary surveys, and I think we'll talk more about why we do have so many mappings of it. We had to go back and take some extra images. And so I think we'll talk a little bit about that, and we love to practice. We've been practicing for our sample return, and we practice for our tags. So you'll see our checkpoint, our match point rehearsals. That's what those were.
Fantastic. And I told you that it was small, but I didn't tell you how small. So the asteroid itself is a little under 500 meters in diameter. And to give you a sense of comparison, although a little bit upside down, here's the Eiffel Tower standing at 324 meters tall. So not quite as big, but still not bad. I was in Paris this summer. I got to stand under the Eiffel Tower. I was doing a lot of planetarium work, and I didn't get to appreciate it. Now I'm trying to, but I'm still working. I don't know. All right. So let's now take a look, though, at some of the initial concern after arriving at Bennu, which was a little bit perplexing. Again, Bennu as the trickster.
And then we went into orbit. That was New Year's Eve of 2018. And within a week, we saw the surface of Bennu explode. And we saw particles flying off into space. And the pictures were really dramatic. And we thought, oh my goodness, the spacecraft safety is at risk here. We might need to get away from the asteroid, completely change our mission plan, delaying everything by months at best. And this turned out to be an example of how microgravity really messes with your mind. Even though these looked like dynamic events, you got to remember, Bennu's only 500 meters in diameter. The acceleration due to gravity at the surface is about what the astronauts experience on the International Space Station, essentially a microgravity environment. So it doesn't take a lot of energy to kick particles off the surface, and everything in Bennu is a slow motion ballet. So the particles turned out to be moving at centimeters per second. They would go into orbit, they would move around Bennu sometimes for days, and then they would fall back on the surface. So there was no risk to the safety. It was just these dynamic photos that sent us scrambling. And it took us a few weeks to figure out that this actually was just a cool science experiment and there was no risk to the spacecraft.
All right, so we're going to go back to Bennu now. And as we do, I think it would be good for us to get a little bit up close and personal. And we're going to hear again from Dante about just the mapping of the surface and a little bit of the wow.
In addition, we mapped this asteroid at unprecedented resolution, both with the camera systems and with the laser altimeter, which gives us 3D topographic maps of the asteroid's surface. This is the highest resolution mapping of a planetary body ever achieved in human history, in stunning detail, which I'm sure you're enjoying on this Planetarium show right now. The other thing we did is we had to make the guidance system autonomous because we had to fit into really tight areas, much smaller than we originally designed the spacecraft. We made it smart. We uploaded a catalog of features, some of which were as small as just a few centimeters across, so that when OSIRIS-REx was flying over the surface of Bennu, it could take pictures, it could compare those pictures to its memory, it could recognize features on the surface and determine how far off track it might have gotten, and fire its rocket engines to accurately target the center of our sample site, which we nicknamed Nightingale. So when we first launched the spacecraft, we had a guidance accuracy of 50 meters. We knew right away that was not going to be nearly good enough to get into the tight areas on the surface. At the end of the day, when we went down to collect the sample, we landed within 73 centimeters of our target location, an unprecedented feat in planetary exploration.
So unprecedented, absolutely. But before we talk about the landing site specifically, we at first actually had to choose, and I say we like I was involved, which I was not. But the OSIRIS-REx team had to choose landing sites, and that was very much a challenge. And there were so many good options, so picking one was hard.
It was a big decision. You know, we're trying to figure out what exactly do we want to sample and where do we need to go and how do we keep our spacecraft safe? Because there's a lot of really large, formations up there that we don't want to hit. So we originally down-selected to 4 sites. And we did some flybys over those and looked at those in more detail. And then we down-selected again to 2 sites. And the 2 sites were a little bit of a discussion, I guess I should say, because the backup site, Osprey, we nicknamed everything with birds to go with Bennu. And Osprey was the safer site. It was not nearly as scientifically interesting, but it was definitely a safer option for the spacecraft. So, of course, as engineers, we want to keep our spacecraft safe, but at the same time, we came all this way, we need to get the best science we can. And so we ended up going with Nightingale as our primary site, because even though it was a much more difficult place to maneuver through and to navigate in, it had the best opportunity from our analyses and our images of what kind of sample we could bring back. And so that was why we ended up choosing Nightingale over Osprey. But we did map Osprey just in case we would need it.
So, yeah, thank you. So what what we can see on the screen right here in front of you is the Osprey landing site. So you can see that really bright white rock in there.
Yep.
And in the center of this depression, you can see a little bit of darker material. And so in trying to hit mission goals, right, the idea behind OSIRIS-REx is to better understand the origins of our solar system. And in order to do that, especially if we want the astrobiology spin on this, which we do, obviously, if we can better understand life, that's fantastic. So we want to try to scoop up some carbonaceous material, and generally that's going to manifest as darker material on the surface, but it was thought very much so that this dark material was actually not carbonaceous, and if you look, there's not really a lot of dark material. But it is, again, as Solveig was saying, a very safe option. So as an engineer trying to protect your spacecraft, you say, this is pretty prime. Like, we should absolutely go in here. And if you're a scientist and you say, no, I want the astrobiology, I want the carbonaceous material, well, that's Nightingale. Yep. So let's go look. I'll zoom out just a little bit, maybe quickly at expense of you being ill. And let's cruise over to Nightingale. You'll also notice that Osprey is sort of equatorially associated, so it's sort of right on that equatorial ridge of the axis of rotation. And Nightingale is a lot more polar, much closer to that North Pole in here.
I think also as we head over to the Nightingale sample site, it's important to point out that when we arrived at asteroid Bennu, we found this asteroid that is super rocky and rough and bouldery, but we have instruments on the OSIRIS-REx spacecraft that were designed to get very fine-grained samples. As Dante Lauretta was saying earlier, we thought this was going to be a beachy asteroid full of small grains of material, but then the OSIRIS-REx spacecraft arrived and we found completely the opposite. So now, instead of having an entire asteroid to sample from, we could only select very small sample sites. So we had to focus very heavily on safety, deliverability, sampleability, where are there fine grains of material and where can we access them on this asteroid.
And that's right. And to do that, we also had to develop a new way to map the surface. And so the team worked very hard and they developed this feature called natural feature tracking that took images down, like Dante was saying, very, very small, detailed images of these sites. And the computer then stored those on the spacecraft and was able to autonomously collect the sample.
So, very good points, absolutely. So, I think you watching this on your dome or on your screen, right? Maybe it's a little bit obvious that I've now centered us on the Nightingale site. But if you look around, right, like nothing else looks even remotely feasible. And I know it's really hard to get a sense of scale as to like what are we even looking at. So let me help you out. Mm-hmm. We can give you some perspective with this yellow ring here. This is a 50-meter diameter ring, and this was the original requirement for OSIRIS-REx. So the idea was, oh, if we can land within a 50-meter requirement, then we should be good. But clearly, that is not the case based on looking at the Nightingale site. And I'm going to change our pitch angle just a little bit to give you a little bit more perspective. So using natural feature tracking, here we go, we were able to refine this down to 8-meter diameter. So that's what that green circle is, green ellipse-ish on your screen. And that gets us to a much nicer location on the surface. One other thing that might be appropriate for us to do is to point out that when we're looking at this asteroid, we have wildly, wildly exaggerated brightness for you, because if we didn't, it's so incredibly dark. So trying to find an asteroid in the night is like looking at a piece of charcoal in the night. I don't have the circles. Well, that's not great. Well, in the center, there you go. There you go. There are a region about this far. Just like take your hands and place that on your dome. There you go. All right. So again, we have wildly, I'll try to add this one more time, wildly exaggerated the brightness of this asteroid in order to give you anything that you can see. So to give you an example of a more true color asteroid, very, very dark indeed. All right, so let's brighten this back up a little bit. Okay, so we have also for your perspective, we have a car there on the surface, and this is to scale, and we figure a lot of this presentation has been very much on the Oppenheimer side of things, very gray, and maybe you need a little bit of Barbie in your life. So again, if you're wondering, well, how big would I be? Well, there you are. This is scaled to you. Okay, so let's take a look first off, kind of gaze around the Nightingale site, because we had talked about how Bennu is the best globally mapped object in our solar system at 5 centimeters per pixel in resolution, and the Nightingale site specifically is mapped to 4 millimeter per pixel resolution. So we can see literal fine grains in here as we sort of cruise down to the surface.
Try to add them again. They didn't pop up. The Barbie and the...
Let me try one more time. Let's see. Any luck, possibly?
Some.
Okay, some. So if you've got it, fantastic. If you don't, apologies.
If you don't, there's sort of an area where you see more of the fine-grained material, and right on the bottom right, as soon as you hit the first larger rock, that's roughly as large as one astronaut.
There you go. Yeah, so pick a rock and then, okay, you're probably
Hopefully
close.
that helps.
Yeah, cool. All right, so from here, let's take a look at the actual tag event itself, and we put together a simulation to give you an idea of what the spacecraft experienced, keeping in mind that this entire process was autonomous. It was able to do this all by itself.
On a moving target.
On a moving target.
On a moving target.
Wow.
Bennu is still spinning as we're coming down.
All right, so here, go ahead.
Oh, yeah, so I can say you can see here that we've moved the solar panels into what we call the Y-wing position. If you're a Star Wars fan, you'll get that reference. And our TAG-SAM arm, our touch-and-go sample acquisition mechanism, it's about 11 feet long and has our sample head down at the bottom. And so we very carefully lowered our spacecraft down all autonomously. We didn't do it. It was autonomous through the programming of the team. And it headed down towards the center of Nightingale. And as I said earlier, we do a lot of practicing. And so we had our first initial practice that we called Checkpoint in April of 2020. It was right after the pandemic started, and we had to do it remotely, and the team did a phenomenal job. And we kind of just came down about 140 meters, I think, above the surface, kind of measured our center, and then went back up straight. We did again in August, where we came about 70 meters above the surface and went straight back up. Everything performed perfectly, so we knew we were ready for our October 2020 tag hit. And you can see here from, as OSIRIS-REx is coming down, how it's going to hit the center. If you go, and if you've seen it live, or if you go onto NASA and watch it live, you'll notice a little adjustment at the very end, and that's the autonomy of the spacecraft saying, nope, I'm not quite on center, and it just pops itself up to hit its center point. And as Dante said earlier, we were incredibly close to our target. And so here you can see the tag head coming down, and it's going to make impact. And we actually went a lot farther than we thought. We went about just over 19 centimeters down into the surface of Bennu, and we fired our thrusters to come back up.
And to give perspective again, that tag head is about the size of a dinner plate.
Yep. Thank you. Yeah.
Also, that natural feature tracking system that Solveig was mentioning, the autonomous navigation, that worked so well that TAG-SAM had actually touched down only 3.5 centimeters from where it was predicted to touch. So that's a phenomenal job for a spacecraft that was designed for a completely different type of asteroid.
Yeah. It was just, I still get goosebumps from it. It was just amazing.
And also, you saw, right, as soon as we tagged into the surface, all this debris gets strewn all over the place. And so the material was actually rather brittle, and literally rocks exploded. All this material gets strewn all over surrounding space, and that was a good bit more violent, really, than was expected.
Much more expected. The Trickster, again, right? Trickster asteroid. we found out that the surface was more like a ball pit, you know, very lightly packed, kind of porous in nature, and so we were able to just kind of impact down into it, and it shocked all of us, and we were very excited to get the sample. In fact, do we show that here, the sample?
Yeah, absolutely. So let's take a look. Let's take a look at the actual video of TAG from OSIRIS-REx. We'll do that next. Okay.
Can they hear me?
Yes. Yep.
So as you can see, you will watch, and you kind of saw it just adjust up a little bit, and you see all the regolith material just flying everywhere. You see there, it just adjusted itself, and then it kind of smashed in, and material just flew all over the place. And we were able to collect what we hope is a large amount of sample. We won't know exactly how much until it's back here on Earth, but
Yeah.
just impressive.
Absolutely. So pay attention to that rock in the sort of upper left-hand corner, right at impact. And if you're thinking this is too many frames too quickly for me to really pay attention to that, I've got you covered in a second. But look here, boom. Okay, you want to see that a little bit more close and personal? Let's take a look at the moment of impact. We'll sort of go through just back and forth between two frames. So you can see the rock right above it is literally crushed, and these particles just immediately explode out. You can see that rock a little bit off to the left-hand side there, upper left-hand side, is getting pushed out of the way, and it's pretty big underneath.
Mm-hmm.
So again, that's about the size of a dinner plate as well.
Yeah. So very impressive. And so this was our TAG event, and this is where we collected our sample. And we collected so much sample that it started escaping.
Yes, and actually, so let's
I'm so sorry, yeah.
Let's look quickly at the process of capture. So the idea is that you've got this nitrogen gas that basically flushes the material up into the tag head itself.
Stirs it up, yep.
And this was thought to be needed because hard to say what the surface composition is like. But because it was so porous, because it was sort of like this ball pit, there was absolutely no trouble with any of this. The nitrogen really stirred everything up, maybe even more so. And so as a result, let's take a look at what some of our first view of the tag head itself looks like.
These were our first views of the sample head after we'd collected the sample, and you can see there's material flying all over. And you can see kind of there's the mylar flaps that help hold that on the inside. And so you can see there's some particles kind of stuck in those mylar flaps. You can see, you can't see through it. Usually you could see through this, and there's no sunlight coming through that. So we know it's got sample in it. And those circles that you see on the top, those are similar to a Velcro pad, and those were thought to help maybe grip or grab some larger particles maybe just on the surface as it impacts. And so you can see on those that there are some samples on there as well. And so we have a team at Johnson that's going to specialize in removing those and studying those as well once we get it back here on Earth. But you see there's so much material flying around that we were afraid we were losing it. It was flying out of the sample head. We had so much material, and so we had to stow it very quickly, much more quickly than we had planned to. But we put it in safely, and we sealed it up, and do we have...
We have that as
Am
well.
I jumping ahead? I'm sorry.
A little bit. It's okay.
I'm sorry.
It's good
I get
thing.
very excited.
Yeah, absolutely. So I guess the one thing I want to say before we jump on is that the idea, right, was you have this material, but how much do we have? How do you figure that out? Well, if you take the tag arm and you rotate that sample head, then you can figure out, based on basically momentum, how much mass you have in there. But if it's not closed, you can't do that, right? Like, it could be all spewing out into space. And so the decision was made that, it sure appears like there is a heckin' amount of material in there. We should just go ahead and close this up. And so that's exactly what happened. I keep saying we like I was involved. I'm just excited to tell you about it.
That's okay. And here it is, and this is the last time we saw it before we open up that capsule again. And this was taken on with that camera suite I talked about in the beginning. And we're going to try to use that camera suite to take pictures as it jettisons off as well.
All right, so one last thing I want to show you, perhaps, is a look at the post-tag surface, right? We've already gone down to Nightingale. But here's a look at the surface. And so basically, I think that the big takeaway here that you can see is that it really left an indentation. It left its own little crater from this impactor on a world that, again, gravity so weak. And as a result, just that little impact caused things to really be strewn out into space. And all on the sort of surrounding landscape.
Yeah.
So where do we go from here? Where do we go from here? Well, we have to bring it home, right? The idea behind this is it's an explore mission to analyze all this material, but also it's a sample return mission. And so after October 20th, 2020, we had a little bit more mapping of the asteroid itself, just to kind of have some fun and shore up some things, do a little bit more science, and then it was time to return home. And for the last, I guess, year and a half or so, we've been, or excuse me, 3 years, I can't do math. For the last 3 years, been cruising through space and headed back to Earth to bring this back to scientists here at NASA, but also we're going to share with friends around the world and better analyze all this material. So this is really the moment that you've been waiting for, is me to show you an idea of what that looks like. And if you're watching on a dome, wow, is this going to be pretty. If you're watching on your phone, wow, is this going to be pretty. Okay, I'll stop talking.
Yeah, we left Bennu May 10, 2021. So this is the exciting part. This is where we are coming back home. And so a lot of you are asking, well, how are we going to get this sample back to Earth? The spacecraft is going to jettison that capsule, and you can see it here leaving. And so that's going to happen at about 4:42 Mountain Daylight Time is when it's going to release that sample capsule, and it's going to start heading towards Earth. About 20 minutes later, OSIRIS is going to fire its thrusters to set course away from Earth. It's going to be its first divert move, and that's where it's going to head towards Apophis, which is the follow-on mission. At 8:42, so several hours later, the sample return capsule will enter Earth. You'll see it here flying over San Francisco. And it's at an altitude of about 84 miles, traveling about 27,000 miles per hour. And about a minute later, it'll reach its highest temperature, around 5,000 degrees Fahrenheit. At 8:44 a.m. on Sunday, Mountain Daylight Time, our drogue parachute will deploy. And that'll deploy at about, let's see here.
Actually, and
oh, wait, I'm going too fast here.
Let me mention, too, that it looks like you've got this, like, stream of emission from a thruster. That is not the case. This is ballistic at this point, so we're coming through sort of just through casual momentum, and here's our drogue chute.
Here's our drogue chute at just over 1,000 feet in altitude, which is pretty cool. And then at 8:50, we will have deployment of the main capsule parachute. And that's what's going to bring it down to Earth. And once it gets down, it'll land in the Utah desert. We've been tracking it. We know exactly where it's going to land. And it's going to land out at the Utah Test and Training Range in the Utah desert. And then we have teams ready to bring it back. So we have helicopter teams that have been practicing for months, actually, to make sure that we get it safely back towards the clean room. We have temporary clean rooms set up on site. Once we have it all contained there, we're going to put it on a military transport, and it's going to go down to Johnson Space Center in Houston, Texas. And there, the curation teams are going to begin to unwrap it, open it up, and we have a whole set of procedures that we've been practicing, and we're going to be ready to go. I believe we'll be able to, we're hoping to have it, some of the sample revealed middle of October, October 11th, no, 13th. Sometime that week in October is when we're hoping to have it revealed.
Also worth mentioning, too, that you may have seen that it is pretty cloudy in Utah right now, and those were actually live clouds that you were looking at. And so even if it is bad weather, that's been practiced for as well.
Yeah.
So regardless of rain or shine, we should be a go, and the excitement is very, very real. So let's learn a little bit more about the sample. will head to Earth to take a look at that.
Stardust mission, which brought back particles from Comet Vote 2, brought back maybe a milligram, and that changed our understanding of solar system formation. So 60 grams is a lot, which was the whole goal, to bring macroscopic large amount of sample back. However, the sampling was way more successful than we had planned. The TAGSAM head, that is there's basically like a backwards car air filter on the end of a 3-meter long pogo stick that sits on the bottom of the spacecraft. It turns out that because the surface is so soft, like a children's ball pit, barely held together by gravity, or freshly fallen snow, if that feels more at home to you. The spacecraft went in, the TAGSAM arm went in about half a meter into the surface. And so the entire TAGSAM head, the collection head, was buried when the gas fired to simulate the regolith and capture the material. That's an ideal situation. So we expect that the sample head was packed with material. Unfortunately, it was so packed that it was actually jammed open. There were rocks that didn't fracture, that didn't powder, that held open the check valve and allowed material to escape. So we lost a lot of material that we would have captured. As it is still, though, our estimate is 250 grams plus or minus 101 grams that we collected. That's based on measurement of the spacecraft movement as the arm was rotated to take a picture of it and see all this material escaping. So well more than 60 grams. It's a huge bounty. It's really a lot of material for some of the work. Now, the organics works that's very mass hungry, because the techniques look for very small levels of compounds, but other methods, for them, a 1 nanometer particle, or 1 micron grain rather, is too big. So they have to slice it up. And so for them, this is an infinite amount to study.
Data one.
To collect samples that first week. And that really depends on the nature of the material that we won't know until we open up the science canister. My expectation, based on the nature of Bennu's surface, plus the fact that we were leaking sample right at the time that we stowed, is that there'll be some dust coating the surfaces that'll be immediately visible. And our plan is to collect some of that material and get it into the analytical laboratories that are available to us at Johnson Space Center.
We'll be taking some of that material and doing what we call a quick look study, where we have a team doing some mineralogy and petrology spectroscopy of the sample within a week to give us some information on the type of how this compares to the meteorites, some basic triage information that we'll have. It's a random sample, but it's going to be very, very fast.
We have an interesting challenge because NASA has another big asteroid mission that's supposed to launch starting on October 5th. So we're going to kind of go quiet. We're going to let our friends that are flying the Psyche mission have their moment of glory. And then we'll come back into the spotlight. The plan right now is on October 11th. We'll be releasing the first results of that quick look analysis, giving people an understanding of how well did we do? Did we predict the nature of this material, or did Bennu trick us yet one more time?
After that, it becomes more meticulous. Taking the sample head apart, documenting every stage will take about a month. And then sample, since the science team has access to a quarter of the sample, and make sure that the science team doesn't either take something unique and rare and deprive the rest of the world from that, or grab just something really boring and well, boring for me, interesting for someone else. Everything will be interesting, but to make sure that we choose intelligently what to pick. So that takes some time. And again, in my case, my organic analyses are destructive. We take the asteroid and we powder it and extract it in solvents. And so since that destroys material, we want to make sure that we pick the right sample such that no asteroid dies in vain. One of the most exciting things about the mission for me is that nearly 3/4 of the material that we bring back is not for the science team, is for the world. And so scientists, perhaps not yet born or in your audience, can make life choices to become qualified to analyze these samples and ask questions that we hadn't thought of. So, as an illustration, a woman in my laboratory, Jamie Elsula, led a study on Apollo samples, collected Apollo 16 and Apollo 17 samples that were stored at Johnson Space Center for 50 years. She was not yet born when the samples were collected. Using an instrument and a technique that was not invented when the samples were collected, to be able to answer questions that could be thought of but had no way of addressing in the 1970s. And so we'll have a fraction of material which is stored frozen and will be archived for 50 years so that future technologies can look at that, and frozen to keep them from changing. But other samples will be just stored in nitrogen in sealed containers, and they can be requested through the usual processes, same way you request Apollo samples or Antarctic meteorites, and write a proposal, get your sample, do your science, and make new discoveries, rewrite the textbooks.
Well, all I can say is, wow, right? How much awesome can you get out of a mission? Like, it doesn't get much better. Sample return coming to a desert near you, or at least a desert near me, in a couple of days. Wow. But it's not over, right? The OSIRIS-REx mission is continuing, and actually under a different name. Ooh, it's very dark, so now we're glowing. But let's dive in a little bit more to OSIRIS-APEX, with the goal of going to an entirely new world. Let's hear some more.
I am the principal investigator for the OSIRIS-APEX mission. So for the OSIRIS-APEX mission, I will be leading the scientific investigations. And as the principal investigator, I have oversight into the engineering and operation of the spacecraft, our overall mission systems engineering, our navigation, and so forth. But a lot of that work has been delegated to our partners at NASA's Goddard Space Flight Center. And so primarily, I'll be looking over the science investigation and ensuring that everything we do as a collective team is to support our fulfillment of our level 1 science requirements. So the science that we have promised NASA that we will be able to complete with this extended mission. So after the sample is returned, the OSIRIS-REx spacecraft is going to start a completely new journey. It will be dubbed OSIRIS-APEX or the OSIRIS-Apophis Explorer, and begin a new trajectory through the inner solar system to eventually rendezvous with an asteroid called Apophis that makes a very close encounter. One of my colleagues recently referred to this as a buzz cut of the Earth in 2029. So at that time, Apophis is going to get within 1/10 of the distance between the Earth and the Moon. And we know that the Earth's gravitational tug is going to affect this asteroid in a couple of key ways. So we're really excited that we get to recycle our spacecraft, our launch off this planet, and all the incredible scientific instruments that we have developed and really learned how to use and characterize over the years to start a completely new journey and study a world that is similar to Bennu in many ways because it's a small asteroid, but also very different. It makes these regular, super close encounters with our own planet, and it's compositionally distinct. So we know that unlike Bennu, which was full of organics and water-bearing minerals, this is a more stony object and probably represents different processes that were taking place during the earliest days of the solar system.
Okay, so we should probably go back, though, to conclude a little bit, to our fearless asteroid, fearless because it's not alive, to be fair. And wow, is it beautiful. So we were talking to our various mission specialists about, what their favorite success was, or just name the successes. And we had to cut these videos down so much because they just kept elaborating about the awesome this, the awesome that, and so on and so on. I think it really is a great testament to every single person involved in the OSIRIS-REx mission as to how incredibly successful this has been. So let's dive into some of the main mission successes.
It's been full of surprises, full of anomalies that we've been able to overcome. We did our sample collection on a different procedure on a much smaller area, 8 meters instead of 50 meters during a global pandemic. There were internet outages, blizzards, fires, train wrecks, all kinds of things that we overcame that you don't really anticipate when you design a mission. But all of that we launched on time and under budget. And we've continued to have an excellent track record, and that will continue.
OSIRIS-REx has literally set world records. We have 2 certificates on our wall from Guinness, one certifying that Bennu is the smallest object ever orbited by a spacecraft, and that we had the closest in orbit ever achieved by a satellite before. So I'm really proud of that. I can say I have 2 world records, although technically Bennu has the first one and OSIRIS-REx has the second one. Stress level has increased every day as the spacecraft has got closer and closer to the Earth, until we performed the final operational readiness test, where the whole team went out to the Utah test and training range and rehearsed every step of the process. As soon as that was done, a lot of my anxiety kind of slid away because I knew we had passed every test. We had gone through every rehearsal. We had gone through critical reviews. Everything looks exactly as we hoped it would. The spacecraft is healthy, functioning entirely normal. So I was like, we have done everything we can do to make this succeed. And that's when I start to relax. I was like, we've done our job. OSIRIS-REx has a history of doing everything really well. And I just feel good that this team is ready to go.
Excited and nervous. Excited because it's everything's going so well. Nervous because one of my jobs is to think about everything that can go wrong. And also looking ahead at the next 2 years are going to be a lot of work because we have this limit of time to do all of our science. And we promise to a lot, and we'll get it done, but it's going to be a lot of work to make sure we can get everything that we want to get done within the span of the end of the project. But also excited to be able to release samples to the world, to be able to interact with the public and the scientific community and tell what we've discovered and get new ideas about what we didn't think of.
Just knowing that we're about ready to get this treasure trove of scientific material down in a few days is so exciting, and just something that has been in the works for many, many years.
All right, well, yeah, thank you for that. And just to echo everything they said, this team has just been amazing, and it's been about 15 years, I think. We had a first announcement of opportunity to go to see an asteroid, a carbonaceous asteroid, in 2011. And the team has been working since then to develop, design, launch, do all the on-site operations, and then bring it back. And like Jason was saying, it doesn't really end with that sample coming home. We're going to do some analysis on it over the next few years, and then we're going to hold it so that future generations. So, if anyone's interested in cosmochemistry, astrobiology, or anything, this is the mission to help with.
Absolutely. And so, this is basically the end of our live stream, but it's really the beginning for this exploration of origins of our solar system, of trying to better understand astrobiology, trying to better understand how we can keep people on the Earth safe from these things, and so much more. There is so much excitement to be had around this mission, and we are just extremely excited to be able to share this moment with you. But before we conclude and before I thank all of you, I think I have one more message to share.
I think it's important to acknowledge and thank the U.S. taxpayers because they paid for this mission and it really belongs to you. And we take that very seriously. We've worked hard to be efficient with all of the resources that we've been provided. And I want everybody to understand the real value of programs like this. As amazing as the science and the engineering is, it's the inspiration, right? And I want the young people in the audience to especially know that we need you. The future needs you. These kinds of missions are out there. If you're excited by OSIRIS-REx, go into science, go into engineering, and there's a lot more skill sets that we need. We have graphic arts, we have video production, we have business managers. All of these are essential to making a mission like this succeed, and we couldn't do it without you.
You heard him. I couldn't have said it any better. So what I will say is thank you. Thank you to everyone from the OSIRIS-REx team who made this amazing thing an opportunity, a humongous success, and thank you to all of you for joining us today, whether it's this evening or in the morning. We're very grateful to all of you, and if you want to share this presentation with any of your family and friends, and whoever, the public, please do. There is a live stream link that you can go check out. And if you follow Rocket Center USA social channels, it's there. If you follow Cosm social channels, Experience Cosm, it's there. Go check it out. So a big thank you to our team, for making this happen, and from our team to all of you. So again, on behalf of the Intuitive Planetarium at the U.S. Space and Rocket Center Home of Space Camp and Cosm Inc. here in Salt Lake City, thank you so much. My name is David Weigel. I hope that you continue to stay excited with this awesome mission. Goodbye.